All right, it's as if we perfectly planned this, because next up we have Richard from Dendra, and Richard's going to spend time actually talking you through the importance of data curation and how important it is to actually curate proper data so you can turn your messy data into AI gold. So please welcome Richard.
Thanks for that intro, Dylan. And yeah, today I'm going to be talking about data curation, which is probably not the sexiest thing we're going to hear about today, but I think it's an important topic that's often overlooked. So I hope you all are not too hangry for lunch. I know I'm the last talk before lunch, so I'll get going. So for the benefit of people that are more of a software engineering background or product background, I thought I would contextualize my talk a bit by talking about how ML is a little bit different from typical software. So in typical software, you have some code, that code has some behavior, and if that behavior doesn't match some specification, you go back to your code and you keep on rewriting it until you have desired behavior. Machine learning also has code in the form of the model architecture, which it's typically written in something like PyTorch or JAX or whatever. But in addition, there's the data that you use to tune your model to get some behavior. And typically, when the model doesn't have the behavior that you want, you don't really iterate on the model architecture. Sometimes you do, but typically what you're doing is iterating on the data. So in a manner of speaking, data is kind of like code, and it's really important to curate your data. If you don't, then bad things can happen. So you're probably wondering at this point, why should you should be listening to me about this? So I work at Dendra, where we work on ecosystem restoration using AI. So part of that is using these heavy lift drones to do seed spreading. We plant trees and shrubs and all kinds of native plants. And in addition, we do ecosystem monitoring using this UHR aerial imagery. And my job is more on that side of the house, the ecosystem monitoring. So we take that aerial imagery and we're trying to classify what are all the invasive and native plants and animals that are in that imagery, as well as infrastructure, all kinds of, whatever are the things that are out there on the sites, and then distill that into insights and what have you. So this is a challenging problem. There's over 1 million plants and animals that have been described in the world. So it's a very long-tailed distribution. And so I spend a lot of the time thinking about sort of data problems in order to improve the machine learning models. So I'm going to make a kind of bold claim that more than 90% of your time is typically spent on data problems, like that is after the model is in production. Yeah, it's important to get that piece of the puzzle right. So for the rest of my talk, the way that I've structured it is sort of like challenge, solution, challenge, solution, challenge, solution. So the first challenge I wanted to talk about is that the training data should represent the stuff that it's going to be seeing once it's deployed. Otherwise, the behavior can be undefined and you can have bad things happen. So here's one story about someone that used Smart Summon on their car at an airport, and it just crashed right into a plane. Luckily, there's no people that work at Tesla Autopilot in the audience. But fundamentally, what happens here is that you train the self-driving car on traffic data, highways, pedestrians, bicyclists, all that stuff. They didn't have a lot of data on airplanes in that training data. And so literally the model was blind. It didn't have the pattern recognition capability to even see the plane, and it just crashed into it. There's different ways of detecting so-called out-of-distribution data. There's these label-free and domain-agnostic methods, which unfortunately for a 20-minute talk, I can't really dive into them, but feel free to chat with me afterwards if you want to get into the nitty-gritty. But typically, you can't avoid sort of these handcrafted rules to detect when your model is misbehaving, and you got to rely on your expertise, unfortunately. So, for example, at Dendra, we do something like geofencing species. So we know, for instance, that kangaroos are in Australia, and if your model is in the UAE predicting kangaroos everywhere, most likely it's having false positives. Or we have a good idea based on past history, like at what frequencies certain species occur. If your frequencies are way above that, likely you have a bunch of false positives. As a self-driving car example, one way that you can detect these sort of out of distribution samples is if you're like, let's say, approaching a stoplight and the model predicts that the stoplight is present, and then the next instant it's not present, and then it's present again and not present. That is an indication. We know from physics that objects don't come in and out of existence. So that's an indication that the model is struggling with that data, and that you should harvest it and add it to your training data. So another challenge, as we just heard from Christina's great talk, is that models can reflect biases in their training data. So I use biases here in a very kind of loose way. But we heard about how there's this myth that models, they're big data engines and they're unbiased. They're not like humans that are fallible. And the problem with that is that, of course, your training data can have biases, and they're not always explicit biases. Explicit racist or sexist or whatever content in your training data, but there's often these implicit data biases. So as an example of that, if you just scrape all the internet's data and you train something like ChatGPT, it might learn that doctors are males and lawyers are male and things like that, just because most of our written text, when it's referring to a doctor, it's referring to a male doctor, right? And so the models can kind of pick up on those correlations and become sexist or racist or whatever from just that basis alone. Models can also memorize these sort of random correlations. So in the early days of like DALL-E 3, if you try to get it to generate a picture of a hot dog, it was just incapable of generating one without a hand in it, right? It just had entangled the concept of a hand and a hot dog and could not disentangle them. And the reason for that, of course, was that all the training data for hot dogs was of someone holding a hot dog. So it had no way to disentangle them. Another example of this is like people that have tried to classify abusive tweets on social media. Like it'll end up sometimes learning like words like umpire are abusive terms just because they co-occur a lot with other abusive terms. So things like that. So you have to be very careful about these sorts of ingrained biases. There's these majority biases that we talked about over and under representation in the last talk, but these models kind of struggle to learn rare phenomena, and if it's just absent in the data, it's going to struggle with it especially. So a lot of this stuff is covered in this great book, Weapons of Math Destruction. And there's this one last one that's selection bias. And to piggyback on the predictive policing example, for instance, these predictive policing algorithms would never dispatch a police officer to one of the high power bankers that architected the financial collapse, right? Like we know that our justice system is not, there's some things are under policed, some things are over policed, and in the historical data, you're not going to see any of these people that have been persecuted, lacked prosecution, that they're going to all of a sudden the model's going to be just in that way. So in that way, it's like a self-reinforcing, like it echoes what it's been fed. So there's this great paper called Changing the World by Changing the Data, which talks about how you can kind of counteract some of these biases by synthetically augmenting your training data. So, people like OpenAI do this where they'll get these, they'll synthetically generate sentences of female doctors and different racial compositions and things like that, and kind of train the model in an alternate universe where these biases don't exist. And that's one way to kind of counteract these biases. But there's other things that you could do. You could the best option is to just collect more data that counteracts that. And typically, real data is better than synthetic data. But sometimes that's just impossible. Like if it's rare medical cases, there might literally not be any more cases in the world. There's other schemes like oversampling rare scenarios or reweighting your gradients, but I'm not a big fan of these. They tend to make your model overfit. It's not as good as having more data. So there's some really cool work coming out in this right now in the image domain where you could get a sample from your data set and it'll create different sort of versions of the same thing while maintaining the semantic content the same. So here it's generating multiple flavors of the same train image. And you could even do things like combinatorically mix and match different concepts. Like, you could subtract a car, add snow, whatever. So if you need to pad your data to kind of disabuse it of certain spurious correlations, you could do that these days. Another challenge I wanted to talk about is that it's not always the case that more is better when it comes to data. Some data is better for training your models than other things. So this is for various reasons, like models stop learning from very easy samples, or like if you have too much perceptual similarity in your data, like too much semantic similarity, that can cause problems. And there's just a lot of plain junk on the internet. So here's some examples of, recently there's been a snafu with the Google AI overviews, where just, there's a lot of shit posters on the internet. And so it can, yeah. So there's a lot of things that I can highlight here. One of them is this paper called SEMdedupe, which is short for semantic deduplication, where they showed that you were able to get the same model performance with a subset of the training data. So just orienting you here, x-axis is training time, y-axis is performance. The orange curve is training on 100% of ImageNet, and then they threw out 50% using their method and were able to match that performance and even exceed it. So another example of this is FineWeb EDU, which they took another data set called FineWeb and basically sampled it or filtered it for the most educational content, and were able to match and exceed the performance of the whole data set. So what's remarkable about this is, I think it bears repeating, is that this is a subset of FineWeb, right? So they took a big data set, they got a small subset of it, so it's less data, and they were able to match the performance with 10x less compute, and then it kept on growing. So I think this is a really cool result that highlights this. So how do you do this sort of thing? There's different schemes. One thing that doesn't work is random subsampling, because whatever's in the majority before stays in the majority after. In the case of SEMdedupe, what they do is deduplicate based on embedding similarity. So let's say this is your reference image. If you have like something that has a very similar embedding vector, like almost the same, they tend to be like either perfect duplicates or almost perfect duplicates. If it's a little bit further in embedding similarity space, it's a perceptual duplicate. So in this case, it's a slightly different camera angle, but same lighting, same subject. And then you go a little bit further in embedding space, and now you have redundant data. So this could be like if you have a picture of a golden lab at a park, and then you have another picture on a different day of a different golden lab at a different park. They're semantically in the same neighborhood. They're not like complete duplicates, but the amount of new signal that the model gets to like kind of update its beliefs around the world is kind of minimal. So the more diverse your data set is, the more effective each sample is going to be, the more like bang for buck that you're getting for your training. So that's SEM-dedupe. With FineWeb, what they did was use more of like a classical deduplication algorithm that works on text. And then they created an auxiliary model that scores the documents for their educational value from 0 to 5. And then it just kept things that were 3 or above. And you know, that they got really good results with that. So wrapping up my talk, you should think of your data as code and really, oh, I got 10 minutes? Wait, that's for 30 minutes. Yes. Oh, okay, yeah, I was planning on 20 minutes. Okay, cool. So data's code, curate your data. And then good data, it's, you know, it's more important to have a very good data set than to like always be chasing the state-of-the-art model. And then models can, you know, learn biases and spurious correlations from their training data, so you have to be very careful to, you know, constantly be padding out your data and getting rid of those edge cases. And finally, you know, the properties that you want in your training data set is that you want it to be representative of your like real world scenarios, but at the same time, not too boring, right? You want it to be very diverse. You want a lot of semantic and perceptual variety in your training data. So yeah, with that, I'm ready to take some questions. Here's how you could find me. And yeah, for a second I was afraid that I was just like speaking way too fast, and yeah, it was 20 minutes, bang on. Question? I got the microphone.
Talk about synthetic generation of data summary. I work in an educational setting where we're training on data sets. Like I'm thinking in my domain, that probably doesn't count. I don't want to generate synthetic educational data, but just talk a little bit at a high level about where that's applicable, where it's not, and just what that process is like.
I don't think that there's any one-size-fits-all here. What really matters is that the synthetic data isn't like too uncanny, right, or too fake-looking. So sometimes, for example, if you're trying to, in my use case where we're using aerial imagery of ultra-high resolution images, that data set just, there's no public data sets of that, and the ones, well, there are a few, but they're very tiny, right? And we have, you know, our internal data sets like over 100 million images, right? So like you can't, if you were just to bootstrap, you know, all the data that would be generated out of any system with like public data is just gonna be hallucinated garbage. So sometimes it's just not possible, right? Like for medical cases where there's very few ground truth samples, it's probably not gonna work, right? But in some cases, like for example, Tesla, I'm sure we're going to hear about this later. For the in their system, they have a entire like game engine basically that can synthesize all kinds of different scenarios. They change out the trees, they change out the lighting, they add, you know, rain, whatever. And so for the same exact like street somewhere, they just randomize all the variables as much as possible, so the model learns to ignore all of these kind of nuisance variables and focus on the salient things.
So in cases where there's well-documented data on a given domain or field, even if it's like scientific and research, is it possible to have synthetic?
Yeah, absolutely.
data?
So one place where this is actually doing really well is with math theorem provers, because there's these domain-specific languages just for proving math theorems. And so you could have these machine learning models that are trying to solve math theorems, and you know right away if like you're making an illegal statement or if the theorem is not proved. So you have this source of ground truth. And so, you know, you have these models that are in a kind of closed loop where they're playing a game where they're trying to improve their theorem proving capabilities. And so, and they're able, you know, there was not a huge amount of training data to begin with, and they were able to just, create a huge corpus of theorems that then they could, use to bootstrap a model. So if you have a way of making very high quality, truthful training data, then you're off to the races. But that could be a challenge.
Cool, thank you.
Mm-hmm.
Hi, my name is Hannes from Digits. Wonderful talk. Thank you for sharing the insight. I was wondering, have you had a chance to work with data versioning tools?
Yeah.
Yeah. Which ones would you recommend?
So I've used a bunch. The one that we use quite a lot is Metaflow. Metaflow lets you, it just has very elegant, artifact tracking by default, and we have some tools that let you, from any, like let's say you have a model and you want to interrogate like what hyperparameters are used or the exact kind of like snapshots of each data set. You could go through the whole lineage and fetch any artifact within that lineage. And yeah, then we have some internal tools to kind of see how things change over time.
Thank you.
Yeah. Yeah.
My name is Justin Reed. I'm a federal contractor for ERT and I'm also a software engineer for NOAA. And I would like to ask a question about the actual embeddings, the actual SIMD that you're using. What type of algorithm do you use to create the actual embedding of the embedding vectors for that specific algorithm? Because I've done some work with like some basic bag of words type of representation and everything. And I was just wondering, what type of algorithms do you use for that?
So I can't speak about what we use internally, but the paper used all kinds of different schemes, whether they're trying to deduplicate text data versus deduplicate image data, and there's all kinds of very powerful vision models these days where you could just use off-the-shelf embedding. So I think in the paper that's what they did. They just used a strong base model, but ideally, if you have a more like specific type of data set, you would have a model that you've already trained that the embeddings are specific to that data set, but in order to use this MDDup algorithm.
Hey, so for instance, let's say you give your model a biased data set. Is it possible or easy to say, hey, forget everything you know about this, and here's the new data set?
You'd probably just retrain from scratch. There's all kinds of issues with, like, if you have a model snapshot and you're trying to resume training with additional data, you got this phenomena that's called catastrophic forgetting that basically when it learns a new information, it just forgets everything from before. So you have to do things like, almost like spaced repetition, where you're showing it old samples to like make sure that it, you clamp down on that and make sure that it doesn't catastrophically forget things from the beginning. But in most cases, it's probably best to just train from scratch. Yeah.
Are you training on multiple data sets? We've got a system we're training a large language model. We have dozens of various data sets we train and retrain on. Is that a scenario you've worked with? And again, to his point about, okay, if a portion of the data you find is biased or you just want to drop that, what does the process look like? Do you have to retrain the entire model from scratch? Is it segmented, or is it modularized in such a way that you can quickly retrain or drop a portion of a training set?
So at Dendra, we tend to, we have task-specific models. So we don't typically, mix completely different training data sets for one thing, but that's very common in language models where you have multiple data, corpuses that you just kind of pull together. There's also schemes where, like, if you have a model, you can have multiple heads that have auxiliary sort of objectives, and you can co-train across all of those different objectives at the same time and reuse the same kind of backbone for multiple purposes. And it turns out that you kind of have this effect where, the rising tide increases all boats. So if you have these different sorts of objectives, it actually helps. It has this like cross benefit from different tasks. You get a stronger base model. But yeah, I can't like speak too much about what we do internally, but yeah.
Great. Thank you.
Awesome. All right, one last question.
Thank you. Very interesting talk. I'm curious if you could tell us remind us again what the AI model is doing for you at Dendra. Like, what is it? Is it assigning treatment plans per acre? Is it helping you plan the flight paths of the drones? And what is it helping you do and saving you time? How's it saving you time?
Sure, yeah. So we have a bunch of different models for different use cases. My sort of baby is the species identification system. So we have a bunch of, so this is real imagery that we took, and this is really zoomed out, but if you zoomed in, you could see individual leaves of grass, and it's ultra high resolution imagery. So what we do is we take this imagery, we feed it through a model, and then the model has to predict what species is present. Or, if there's a pipeline or asphalt or a cow or whatever it might be, it has to predict what's present. And then, so that kind of gives you like a census of what's where, and like, we have this kind of Google Earth looking thing that you could zoom around, and if we have like, I don't know, we say you have 30 koalas, you can click on them and kind of teleport between them to, spot check the model if you don't believe it. So it kind of brings transparency into the ecosystem restoration. But then there's all kinds of things that we then present to the customer. So, typically you don't want to just throw a big bucket of data at customers, right? They have decisions that they want to make, and so you try to distill insights out of that and help with decision support. So we might do things like change over time, right? If you're doing seed spreading, people want to know, is it working, right? So you want to see the saplings as they're coming in, all the analytics on that. All kinds of different analytics that people that are land managers care about.
Awesome. Round of applause for Richard.